When we're plotting the results of our sensitivity analysis, recall that the results that we're plotting are based on the concentrations of our reactant over time. So here's where we're determining the limits of our y-axis based on those concentrations. And here's where we're plotting the points on the graph in terms of plotting those concentrations. But recall, these are not the only results we have from our sensitivity analysis. If we go back to the top of this script, here's where we're loading our results. I'm going to put my cursor on this line of code, and I'm going to run only this line of code by hitting the run button. Recall, if I hit the source button, it runs the whole script. If I hit just the run button, it's just going to run the line of code that I have the cursor on, or it will also run a block of code that I've highlighted if I've highlighted some code. So in this case, I just want to run this results line of code. I'm going to put my cursor at the end of that line of code and hit run. You can see in the console, it's run that line of code. And also I have results in my environment. If I click on results, it's going to run view on those results. And remember, I have 3 different elements of the results list. These elements correspond to the 3 different initial concentrations. For each of these elements, I have 3 more elements under each one, and these correspond to the different rate coefficients. So for each combination of initial concentration and rate coefficient, I will then have these results that I generate for each iteration of my sensitivity analysis. That includes the value of the rate coefficient and initial concentration for that iteration, the times for that iteration, as well as these concentrations that we're currently plotting. But we also have these filtered concentrations. These are only the concentrations that are above 1% of the reactant remaining. So if that's the data we're actually interested in, we want to plot these data as well in our graphing plot. So we can add just a little bit more to our iterative algorithm to have this script run another loop that will repeat all of the graphing that we want to do for both the filtered concentrations as well as the concentrations. So as with before, we want to determine what part of the code do we want to iterate. Well, in this case, it's pretty straightforward. We're basically plotting all of our results for the different initial concentrations and the different rate coefficients with this big long loop that starts here. Here's the beginning of that for loop, and we can scroll down. We can see the end of that for loop where we get to this closed curly bracket for the for loop, and there's the end of that for loop. And basically, that's what we want to repeat. We just want to do all of this, but we want to do it twice. We want to do it once for the concentrations and once for the filtered concentrations. So let's just say I've already got this code highlighted. I'm going to go ahead and indent it because I know I want to put a loop around it. And I need another for loop. And again, I need some variable that's in a vector of values in order to define a for loop in R. And in this case, I can think about the fact that, well, I have different names for the elements of the list that represent the results of my sensitivity analysis. So it makes sense that at one time through this loop, I want to have the name of the element for concentrations, and another time through the loop, I want to have the name of the element for the filtered concentrations. So if I make a vector of character strings, I can say, well, the name of the concentrations is just CONS, and the name of the filtered concentrations is CONS underscore filt, FILT. And then I just need to come up, well, what's the name of the variable that I want to take on these values each time I go through the loop? And I'm going to call that const name for the name of the concentration element that I want to plot each time through this loop. So the first time through this loop, const name will be the character string conses, and the second time it'll be conses underscore filt. So I need an open curly bracket to define the block of code I'm repeating. That's going to be all of this code that I just indented down to here. And I need another curly bracket that will be the end of this for loop. So we're repeating all of this material twice. The first time we go through, the value of const name will be constants. The second time will be constants filled. So how do I make use of this in my loop? Now I want things to change according to these names within this loop. And there's two places that I need to change things. First of all, it's everywhere where I have a $CONS. That's where I want to change things. So one way I can use to find all of those is I can go back to the top of my script. I'm going to hit Control F to bring up my search tool. And I'm going to type in $CONS. Because I know everywhere where I'm using $CONS now, I want to make it so that this actually changes each time through the loop. So how do I do that? Well, you have to remember how lists work and how named indices of vectors work. Recall that this $sign is shorthand. I can use, for a list, I can use the double square brackets around the string consts. And this does exactly the same thing as the $sign operator. But now that I'm using the double square brackets, instead of hard coding this string CONS's, I can actually use the variable that I'm changing through my loop, this const name. So let's think again how this works. The first time through the loop, the result it's going to pull is the one that's based on whatever const name is the first time through the loop, which is going to be CONS's, which is the same thing we're plotting now. But the second time through the loop, this const name is going to have the value CONS's underscore filth, which means the second time through the loop, we're going to plot this result instead of this result. So all we have to do is make sure we make this change that we've made right here to all of the places where I see this $sign const. So I can do a next here, and of course it's going to take me to the very next line. I'm going to just copy and paste this double square bracket notation here because I know that's what needs to change. Then I'm going to hit next because I need to change the next place I have $sign const. Oh, here it is. And this is in my points. That makes sense. I need to plot different points each time through the loop. So again, I'm going to replace the $sign notation with the double square bracket notation. Therefore, this will change each time through the loop. So I'll plot something different each time through the loop. Then I'll hit next, and that's actually it. That's all I had to change. So now I have code that should go through this whole process twice and generate a whole new set of graphs that represents my filtered concentrations after the set of graphs that represents my concentrations. So let's go ahead and run this and see how it works. I'm going to go to my product directory and I'm going to open up my visualization. Now, just like before, these are my unfiltered. You see I have all of the concentrations in these plots. And I'll have them for every combination of initial concentration and the decay rate. So my initial concentration of 25, 3 different decay rates. Initial concentration of 50 with 3 different decay rates. Initial concentration of 100 with 3 different decay rates. Now I have yet another set of plots where I have the initial concentration of 25, but now you can see I'm working with filtered data because I don't see any data points after we reach the point where there's only 1% of the reactant remaining. So these two plots are cut short. We don't get there with the lowest decay rate, but for the 0.1 and 0.2 per minute decay rates, we do get to the point where there's less than 1% of the reactant remaining. Same idea with the 50 milligram per liter initial concentration, same idea with 100. And again, you'll notice that these plots all look the same. All we're doing is rescaling the y-axis. And again, that makes sense because these are relative decay rates relative to the initial concentration. So we're going to get to the point where at 1% remaining, regardless of where our initial concentration is. The differences and where we get to 1% remaining are only going to depend on what we set this decay rate to. And that's why these plots look the same, other than the fact that the y-axis is rescaled. So we've changed how our plot works, but our labeling could be clearer. how do we know that we're looking at one of the plots that's been filtered versus one that hasn't been filtered? It'd be nice if we add that to our labeling so that's clear as you're browsing through all of these graphs. So we can minimize this and go back to our code. And we can think about where we're adding our label to each graph. Recall that this particular label in the upper right-hand corner of the graph is saying which initial concentration we have for each graph. So maybe we can just add to this label to tell us something about whether we're looking at unfiltered versus filtered data. And that means we need to add some code somewhere around where we're calling text in order to create that particular label on each graph. So before this text, I have to decide what the label is going to be that I change this text. Now I could just use the string consts and consts in it, or consts and consts filt, that I'm using as the names of the elements of my results list. But I can also use something that's more interpretable in English that a human can understand. These are kind of just variable names and they might be a little bit cryptic to somebody who's looking at this who doesn't know how the code works. So one thing I can do in order to figure out a different name is to translate the name. And in this case, I can use a conditional statement to do that. So I can use what's called an if statement. An if is a conditional control structure in a program, and it's true in most programming languages. You can write some sort of if-then where you say, if something is true, then I want you to do something. So in parentheses, we need to put something that evaluates to a logical value saying whether if something is true, we're going to do it or not. In this case, we want to do a logical operator to say if the variable name, const name, has a certain value, then we want to do something. In this case, if the const name is equal to cons, then these are our unfiltered data. So if const name is equal to consts, my label is going to be unfiltered. Sorry, that's the wrong operator. I want to assign label unfiltered. So the double equal signs indicate that we're using a logical comparison operator rather than an assignment operator. So a single equal sign is used for specifying arguments in function calls or as a particular type of assignment operator. But the double equal sign says, no, that's not what I'm doing. Here I'm doing a comparison. I'm trying to find out if this left side is equal to this right side. So if const name matches this string, cons's, that means those are the unfiltered data, and I want the label on my graph to say unfiltered. And I only have one other option, so I can add to my if statement an else statement. So I've got an if, and whatever's in these curly brackets is going to get run as if what's in those parentheses is true, then whatever's in the curly brackets is going to get run. In this case, I only have one line of code, but I could put multiple lines of code here. And then if you add an else after the if statement is closed, that means you say, I want to do something else if this is not true. And in this case, there's only two options. So if it isn't unfiltered, it must be filtered. Because if it's not consts, then it's going to be consts filt. And the consts filt represents filtered. So this is called conditional programming, and it's central to any programming languages. If-then statements are really common. This is the first time we're using it here. So we're trying to use a conditional to say if consts is a particular value, then we need to use a particular label. I'm sorry, if const name is a particular value, we want to use a particular label. So after this code, we should now have a label that represents what we want to put in the graph if it has one of these two different characteristics. And that's really easy to do because what we've done with bquote is we've made it really easy to insert some R code to put a value in our expression that we want to be rendered in our graph. And we've already done that with this dot parentheses notation. We wanted to put this value into our expression such that it would be represented as a number ultimately in the label that we put in the graph. That's why these numbers are changing. Well, we can do the same thing with the string. We've got a string that's either going to be unfiltered or filtered based on the label. And again, we can use a dot notation with parentheses to specify some R code that will go in this place. We also need to put a tilde here because these are two elements of an expression and we need some space between this element and the first element of our existing label. And we can just type label in here because label is going to be what we want to, the string label is going to be what we want to insert into this bquote expression that will then get rendered into the text in the label in our graph. So I'm going to save this and I'm going to run it one more time. And if we go back, we can see that we now have an unfiltered here. Because this is the first graph. These are unfiltered data. You can see we have all the data, so that makes sense. And we have 3 unfiltered graphs for the 3 different initial concentrations. And then when we get to the next set of 3 graphs, these are all filtered. And we can tell they're filtered because we don't see data after that we get to 1% remaining. And there should be 3 graphs labeled with filtered concentrations.